Hi, I'm Alberto Zanella, an intensivist of Polyclinic of Milan, and I will talk about extracorporeal suture removal, how to improve it using metabolic control. I am a co-inventor of patents related to this topic. So, extracorporeal suture removal is a powerful tool to unleash the relationship between minute ventilation and partial pressure of arterial CO2, and mainly is an extracorporeal circuit, a veno-venous circuit, focusing on CO2 removal, and the indication are preliminary to avoid intubation or fasten extubation in COPD patient, or to achieve protective ventilation in ARDS patient. Unfortunately, although extracorporeal suture removal proved to be effective, it also showed a high rate of complication, mainly related to systemic anticoagulation, as shown in the relevant REST trial, where we can see a reduction in tidal volume, but the trial was stopped earlier for futility, and this was mainly due to higher incidence of adverse events, serious adverse events, almost all related to bleeding and hemorrhage. So unfortunately today there is still an imbalance between safety and efficacy of extracorporeal suture removal treatment, and many questions are still open, and we believe that we definitely need an improved technology to reduce this complication, and also an increase in the CO2 removal efficacy may promote the reduction of complications. So, fortunately, CO2 removal may be clinically relevant also at low blood flow due to the higher extraction of CO2 compared to oxygen delivery. But unfortunately, the threshold of clinically relevant CO2 removal are higher than the blood flow that can be today regionally anticoagulated. Thus, systemic anticoagulation is always required. So our idea is that if we boost the CO2 removal, we may be clinically effective at lower blood flow. And on the other side, if we can increase the range of blood flow for regional anticoagulation, we may end up with a safer technology based on regional anticoagulation while still achieving high CO2 extraction. So our way that we propose to enhance CO2 extraction is primarily acidification, and this is the main topic of today. And the the majority of CO2 is transported in the blood under the form of bicarb, which is in equilibrium with dissolved CO2, which leads to the partial pressure of CO2, which is the driving pressure that brings CO2 out of the membran lung. So if this is the standard condition, if we add, like in the bottom of the slide, 10 milli equivalent per liter of an acid, we see a massive increase of partial pressure of CO2, which of course allow to increase the extraction. So which are the acid that we can use for? Of course, the easiest is lactic acid, a metabolizable acid, which has no harm and easily measured at bedside. Of course, we can also use citric acid, which may combine acidification with regional anticoagulation. But as we understood, the citric clearance is lower than lactic. So in the beginning, we started using diluted lactic acid, and we understood and that of course acidification, a higher acidification, 5 milliequivalents per minute, led to a significant drop in extracorporeal pH, and eventually this led to a significant rise in CO2 with an extraction which went from increases by 64% in our preliminary study. And later on, we applied this strategy for 48 hours, and we introduced the closed loop dialysis circuit, which allow us to infuse highly concentrated lactic acid, and this proved to be effective and safe. Moreover, with this closed loop, we can also move the membrane lung on the dialysate, which is slightly less efficient than when the membrane lung is on the blood, but eventually may be more biocompatible, and of course we can use more big and economical membrane lungs. But unfortunately, the metabolizable acid infusion, if not controlled, without metabolic control, increases the total CO2 production, decreases the pH, is thermogenic, and this ultimately may be not effective in reducing minute ventilation, as demonstrated in this study by Vittorio Scarabilli, who tested 3 different acids in a sheep model, and although the acidification was effective in boosting the CO2 removal, the minute ventilation was not decreased. So the other possibility is to use an acid which does not contain calories, and so does not increase the total CO2 production, like hydrochloric acid. But if you use not metabolizable acid, you need to remove the infused acid. And we developed a strategy to be able to in the closed dialysis loop, we were able to create an acid zone and a basic line, a baseline where moving chloride with the electrodialysis, and this was effective in increasing the extracorporeal CO2 removal, but more importantly was now finally effective in reducing minute ventilation. Unfortunately, the base chamber creates extremely high pH fluid, which has a low safety profile, and more than that, electrodialysis is quite complex. So we tested a similar strategy employing ion exchange resin that aimed at removing sodium and replace it with H+, but also with this technology we needed to have highly alkalotic replacement solution. So even in this case, we were able to reduce minute ventilation due to the high increase of extracorporeal CO2 removal. But also here, the sodium hydroxide infusion was led to transient tachycardia and low safety profile. So here comes the study where we try to put all together, but keeping for the first time a metabolic control. We tried in swine, in 8 swine, we tested three different extracorporeal techniques, one based on lactic acid infusion, two based on hydrochloric acid infusion, and to remove the infused chloride, we use renal replacement therapy, and the replacement solution were based on one test only on sodium lactate, and on the other step half of sodium lactate and half sodium hydroxybutyrate. And of course, through all the study, which were made of 2-hour steps, the total caloric input was kept constant, the glucose constant, PCO2 constant, changing the respiratory rate, and importantly, no highly based solution were infused. So the study has a high safety profile. So this is the baseline. So we use the caloric input required for this wine, 100 kilocalories per hour. And then we added this in the circuit, the membrane lung on the blood. And so you can see the of course, the dark extracorporeal CO2 removal allow a reduction in minute ventilation. And then we added in a closed dialysis loop with a second membrane lung, and we were able to further increase the extracorporeal CO2 removal with a small further reduction in minute ventilation. And then the first boosted CO2 removal based on the infusion of lactic acid on the dialysis loop, and in this case half calories were glucose and half lactic acid. And by doing that, we got a slight increase of total CO2 production, probably due to the thermogenic effect of lactate, but the minute ventilation decreased compared to the previous step. And then the most complex setup is based on hydrochloric acid infusion on the dialysis loop, and then we needed the ultrafiltration, so the renal replacement therapy, 1.5 liter per hour, which is the amount of ultrafiltration required to eliminate the amount of chloride infused with the hydrochloric acid infusion. But unfortunately, the ultrafiltration we lose sodium, and here comes the need for the infusion of the replacement solution, which contain the sodium with the lactate, so sodium lactate, which is a quite safe solution, and the remaining calories needed were given by glucose. And with this setup, we were able to achieve a further decrease in minute ventilation. And now the last setup is similar to the previous, but the replacement solution contained half of the sodium as sodium lactate, and the half as sodium hydrobutyrate. And you see then there is still some needed for glucose to keep the total caloric input. And here we achieved a similar extracorporeal CO2 removal and minute ventilation. And we were able to keep sodium and chloride stable through all the study. And interesting, the sodium lactate, of course, was the most equilibrated step when with the hydrochloric acid infusion, the lactate reached the maximum level. Instead, with the butyrate, we see the base excess dropped further, although with still a minor decrease in pH, but no relevant complications were detected. So we think that this setup combined dialysis acidification with renal replacement therapy, metabolic control, was pretty safe and effective, and this may eventually allow to reduce complication. And thank you very much.